Hey guys, Mr. Briding back here for the third lecture in energy transformations. And what this lecture is pretty much going to go over is the idea of energy conservation and comparing some of the different equations and just showing you that no matter what equation we use, we still end out with a lot of the same products. So in the first one here, they tell us, according to the work that we did, if we use a force of 430 newtons over a distance of 0.95 meters, we end out with a total amount of work of 410 joules. So this is the energy that we put into it with our legs. And then they're saying that, you know what, okay, well, what if we were to do potential energy as mass times acceleration times distance? Um, This ends up being, if we were to do a permutation of this, distance is potential energy divided by mass times acceleration. And all I did was, because mass and acceleration are being multiplied by distance, we want to get rid of these to get distance by itself, and so we did the exact opposite to the other side. And so if we were to divide this side by mass and acceleration, we divide the other side by mass and acceleration, these cancel out, which gives us distance equals potential energy divided by mass times acceleration. So the distance is equal to 410, the potential energy, divided by mass and acceleration, which is going to be 430. So that gives us a distance still of 0.95. So no matter how we try to calculate any one of these variables, because of the conservation of energy, we know that we're going to end out with the same product. And down here, they're pretty much saying the same thing, but now let's say we go to the moon. They're saying, okay, well, your potential energy at the very top is still going to be 410. But to figure out distance, we get we get the potential energy divided by the mass times acceleration. And we just have to go in, rather than acceleration equaling 10, because we did 44 times 10, or 44 times 9.8 to get 430. Now we're doing 44 times 1.6. Alright, and so if we did 44 times 1.6, bring up handy dandy calculator here. So we do 44 times 1.6, and we get 70.4. So now if we were to do that, 410 divided by 70.4, we now get 5.8 meters. So our distance on the moon, given that energy is conserved, 5.8 meters. And that comes close to how he calculated out of, if you were to figure the distance, you take that amount of energy you have and you divide it by the mass and the acceleration. And that is pretty much it for this lecture. I just want you guys to see that energy is conserved, and no matter what calculation we use, we're going to come up with the same amount of energy. But let's say if we're on the moon where acceleration is less, we're going to have a higher distance. Okay, so you look at this little picture here and you see a little guy. On Earth, this is how high we jump. On the moon, this is how high we jump. And you know what? On the moon, the potential energy this guy has here is the same as the potential energy he has here. And the potential energy he has here in the ready position is the exact same as when he's at the very top on the moon, or exact same as it is over here. Alright? If you have any questions, make sure you let me know, write them down, and I will see you guys next time.